that linear function was tau sub f equals to C plus normal stress times angle of internal friction. So remember that we are talking about tau here, which is the shear stress, and you have the normal stress here as well. And we have this equation here, which shows you the strength of the material. Tau equals to C plus sigma line or sigma times tangent of beta. And C was the intercept, and phi was slope of that, and phi was the slope of that. Alright, so this was the estimate of that nonlinear function that we have. Alright, and we talked about the significance of the C value and the phi value. C was cohesion, right? That has to do with the stickiness of the particles together. The better they stick together, the better they provide load bearing in the system, right? That makes sense. On the other hand, we have frictional properties, which is represented by sigma times tangent of phi. And phi, we call that angle of repose or angle of internal friction. That has to do with the interaction of the particles with one another, right? And that phi value, we talked about the parameters or properties that influence the phi value. Remember, for instance, for the case of a compacted material versus a loose material. Which one has a higher phi? A compacted material has a higher phi, better interaction between the particles, or a loose material? A compacted material, right? That was the whole purpose of compacting the material. We want to reduce the void ratio to be able to have better interaction between the particles. Therefore, we have better interparticle contact, better frictional properties. Right? So that's basically how these things are correlated with one another. And then we had, for instance, we talked about crushed material versus rounded material that you can source from the riverbed, right? So for instance, if we have crushed aggregates that are coming from El Paso quarry, they have a better interactions in terms of the frictional properties compared to siliceous river gravel from Rio Grande. Yes. They do have that, right? So that's another way to think about the contribution of the phi value to the strength of the material. By the way, if you look at that equation there, the higher would be the C value, the higher would be the sigma value, the higher would be the phi value, the higher would be the strength of the material, right? The strength of the material is on the left-hand side of that equation. And it has a direct relationship between the C value, phi value, and also the stresses that the material is experiencing. All right, so in very simple terms, we basically subdivided the strength of the material into two components. One component has to do with the cohesion, the other component has to do with the friction, right? Typically for clay materials, you have cohesion that is going to be the predominant factor that influences the strength of the material, right? Clay material, remember, plastic, fine grain material that stick together well. On the other hand, when you're looking at well-graded gravel that you typically use in load-bearing mediums, such as the foundation of this building, those are the materials, or those are the gradations that they have small amounts of fines in it, and even those amounts of fines are non-plastic, right? You don't want to put too much plastic material into a foundation because it absorbs moisture and it expands. Undergoes, remember we talked about the shrinking and swelling behavior of the material, right? So you want to make sure that the foundation is protected against those highly plastic materials. Make sense? That's basically the general concept behind these two components that we have here. So for clay materials, we bank on the cohesion. For the case of other load-bearing mediums that we might have, we are interested in the interparticle frictional properties as we talked about. Remember we talked about the particle top size, geometry of the particles, and the gradations, right? So if in your exam I asked you that you have two systems, one consisted of well-graded material, the other one is consisted of fine-grained soils. Conceptually, can you do comparisons between the C values and the phi values of the two? You should be able to discuss that, right? So that's basically what we have in terms of the parameters of the Mohr-Coulomb failure envelope. So this is called Mohr-Coulomb failure envelope. This line, the equation of the line is tau equals to C plus sigma times tangent of phi. Parameters of the Mohr-Coulomb failure envelope are C value and phi value. Right? Because if I know what the C value is, if I know what the phi value is, I can plot this line. Right? I know the intercept and I know the slope of the line. The rest of it is going to be just putting different numbers in there to be able to get that line. Right? Remember what the significance of the Mohr-Coulomb failure envelope was? Any point below that point was, quote-unquote, safe, right? Remember, you can plot the circles, if you will. Let's assume I have circle A. I have circle B. Comparison in terms of the stress states that they represent. You have two stress states. These are on the, what did we call that x-axis here?
Principal plane.
That's basically the orientation of the principal plane, right? This is the orientation of principal plane because the shear stress along that is 0, right? At any point along this line, your shear stresses are 0. Therefore, that's a principal plane. And that was the definition of the principal stresses. Principal stresses are stresses on the principal plane, right? So that was basically the definition that you had from your mechanics of materials. All right, so you have half circle A and half circle B there. Since it's symmetrical, we always show it with half circles, as you know. One of them is touching the Mohr-Coulomb failure end. The other one is not. One that isn't is A. What can you tell me in terms of the stability of the system that experiences this stress state? It's safe, right? Because it's contained below the Mohr-Coulomb failure envelope. The stress states that are below that line represents a safe condition. On the other hand, if you're looking at a point, the second one, what do we have on the second one? We have a point of tangency, right? So it basically touched the failure envelope. What was the coordinates of the points of tangency? Is this is the point of tangency. I'll put the N here. Stress states at point of tangency represents the stress states at failure. Right? So what do I see here? I see that there is a combination between sigma and tau that resulted in the failure of the material. Is it the maximum shear? It is not. Where does the maximum shear happens? Do more circle again? Exactly, it happens here. Let's call it N. Make sense? So a different combination between the normal stress and the shear stress here resulted in the failure of the material. I remember what this angle was? That's your 2 theta, right? And that's twice the rotation that results in the failure of the material, right? This is the plane of failure. Well, this one, let's call it ON, is the plane of failure. If O is the center of the Mohr circle, ON will be the plane on which the material will fail. Now remember we talked about how you can calculate this theta as a function of C and phi values, right? It was 45 degree plus phi over 2, right? And that's some equation that you should be very familiar with when you sit for your FE test. For some reason they like that equation a lot in that exam. Alright, so that's basically what it means when you're looking at the angle of failure. This is a quick review of what we talked about. And you know how you can calculate the center of the Mohr circle and how you can calculate the radius of the Mohr circle, right? The radius of the Mohr circle is? Yeah, sigma 1 minus sigma 3 divided by 2. This is sigma 3, this is sigma 1, sigma 3. The difference between sigma 1 and sigma 3 gives you the diameter. Half of it would be the radius of the Mohr circle, and also you can calculate the center of the Mohr circle, which is sigma 1 plus sigma 3 divided by 2. So those are the material, those are the equations that we talked about before. Your T8 in this week is going to go over the Mohr circle in the labs, so you can just familiarize yourself with it again. Take a look at the information that I uploaded under this section on your website. There's a Mohr circle slide, a series of slides with some examples. Also, there is a handout. So take a look at both, and this is written in very simple and understandable way. Let's call it applied Mohr circle. We don't want to go into the details of the Mohr circle in this specific case. All right, so that's basically what the shear strength of soil is. The part that we have to be very careful about is that we're not looking at maximum shear stress. We're not looking at maximum normal stress. We're looking at a combination between the shear stress and normal stress that results in the failure of the material. Now the question is, how can I plot or develop this failure envelope, right? So now for that we have different types of tests. Today we're going to talk about the direct shear test, and that's a test that we run in the lab to be able to get the C value and phi value, if you will, to be able to properly characterize the Mohr-Coulomb failure envelope. And in our next lecture we'll talk about the triaxial test. Specifically we'll talk about the triaxial shear test to be able to get the C and phi value. And then we talk about the distinction between these two tests, the advantages of one over the other one, and then we'll see which one would be better to realistically simulate the field conditions. And that's basically an operating word here. When you run the test in the lab, the ultimate objective is to simulate what is happening in the field, right? So you can come up with very elaborate tests, but it's not going to represent the conditions that we have in the field. Specifically for the soils, if you recall in the first lecture we talked about soil has memory. What that means is that if you mess up the internal structure of the material, you end up with entirely different results. It's different from concrete, asphalt, wood, and all the other ones. Right? So we have to be very careful about that. And sample disturbance for us is going to be one of the significant parameters. A few years ago, some of your friends in the senior design project, they were designing a structure. They decided to go in the field and grab a shovel and a bucket and get the soil there and brought it to the lab and run the test. And they came up with extremely elaborate parameters for the strength of the material. But one of the questions that were posed to them was, you disturbed the soil, right? You disturbed the soil and brought it to the lab and compacted the material with entirely different compaction levels. Right? So what happens to the strength of the material? What happens to the interaction between the particles? You're basically replicating a condition that is not going to be representative of your field conditions. So you have to be very cognizant of that. Once we start talking about the settlement of the soil and the pore water distribution in the system, you'll see that a small anomaly in the sample disturbance results in changes in the parameters that you calculate for the settlement of the soil. We call it the pre-compression pressure. Pre-compression pressure is extremely sensitive to the stress histories that soil experience. So you have to be very careful about that. So let's go back and see how we can figure out the C values and phi values. All right, so the objective in our two lectures, today's lecture and the lecture that we'll have on Wednesday, is going to be determining the C values and phi values using different types of tests. And the ultimate objective is to be able to replicate what happens in the field. So keep that in mind once we start talking about the shortcomings, disadvantages of the different types of tests that we have. When we start talking about the slip planes in different types of tests, we're going to go back and revisit those concepts. All right. Yes.
So is today's lecture going to be on Monday's exam or no?
Yes. Everything until Wednesday, 1:30.
So next time the homework is due on Wednesday?
Yes. Yeah, the homework is due on Friday. This homework for this group. So I post the solutions hopefully by Friday night.
I believe on Friday we don't have class.
Friday we don't have classes?
No classes Friday.
So if there's no classes, that's fine. Our class will be on Friday. Not on Friday. Our class will be on Wednesday. Right? Okay.
So we submit the homework.
You can submit your homework before then. Right. What is Friday? What is Friday?
Friday?
Spring study day.
Study day?
Spring, yeah.
Oh, that's great. You can study.
Good Friday.
Oh, yes. All right, so any other questions? This is the previous homework, yes. We're talking about the next homework.
On Wednesday, and that's gonna do Thursday.
So let's do it on Thursday, yes. But RTAs, and I'll be here on campus if you want to submit your homework. All right. Okay, so let's get into our discussion about the direct shear test. All right. Have your TA discussed the direct shear test? No? Yes? All right. So you know the general concept behind the direct shear test, but let me just quickly go over it again, and we're going to go a little bit in detail in terms of the calculations of the stresses and how we can develop our Mohr-Coulomb failure envelope. All right, so the direct shear equipment, or we call this one direct shear box, is consisted of two segments that are split in half, and you can pour the soil in between here, right? So either compact the soil right here or pour the soil in between, and you place a surcharge at the top that represents the confining pressure that you have. We're going to talk about that. And then you impose a deformation from the side and slide this to have segments pass one another. So based on the resistance of the soil against the sliding, remember that was the definition of the shear strength of the soil, we can get the C parameter and phi parameters. So in okay, let me go back again and see what we do in the direct shear test. So in the direct shear test, we have a system, we have a data acquisition system, we have a computerized system, and we have the direct shear box, and we have a system that you can apply the loads. The loading is happening in two directions. One would be applied based on the surcharge, or the weight that you put at the top of the soil here. The other one has to do with the deformation that we impose horizontally, right? And by that I mean that, for instance, you apply a certain amount of deformation per minute. For instance, 0.02 millimeter per minute. That would be the deformation that you apply from the side. So what happens in the beginning? In the beginning, the soil resists the load, right? But beyond a certain point, the soil starts to fail, right? And remember, I need to find the stress states that are on the Mohr-Coulomb failure envelope. I need to take the material to failure. Make sense? I want to make sure that if my stress states falls below the Mohr circle, that's not going to give me the failure envelope. Because for the case of failure envelope, I have to figure out 2 or 3 circles to be able to find the tangent to them, right? because those points of tangency are the points that represent the stress states at failure, right? So you have to take the material to failure. So let's go back and see what we can do with this direct shear test. Initially you apply a surcharge. Let's assume I put 100 grams at the top of the soil. The soil could be loose, the soil could be compacted, right? Depending on which condition you want to determine. Remember, we want to replicate what happens in the field, right? So if the soil is going to be compacted in the field, I compact the soil. If the soil is going to be loose in the field, you have to use the loose conditions. And obviously, as you know, the C value and phi values for the soil that is loose needs to be lower than the one that is compacted. All right, so let's go back again and see what we have here. You have a box that is split in half, and it can freely slide past one another, right? And that's basically how we shear the material. So stage one, place the surcharge. And what's the role of that surcharge in your opinion? You place a surcharge in there, how does that influence the interaction between the particles? Right, so basically once you place the surcharge at the top, it actually influences or results in higher interaction between the particles. So that's basically called the confinement. It allows for the material to be pressed together. Therefore, you have higher load-bearing capacity, if you will. All right, so stage one, place a surcharge at the top. Stage two, shear the material to failure. Why to failure? Because we need the point on the Mohr-Coulomb failure envelope. If you apply the loads and you don't see any movement here, that basically means that you ended up with half circle A as opposed to half circle B. You want to make sure that the material fails, right? And this failure is already determined. Remember we talked about the slip planes, right? What was the definition of a slip plane that we talked about? Remember, any point along this slip plane, the stresses are higher than the strength of the material. That was the definition of the slip plane. And that was how the soil essentially failed. Remember, they were curved in some cases, they were linear in some other cases that we talked about. So here we are looking at the stress states that results in the failure of the material. Where does the material fail in this case? Do you know the plane of failure? Where is it? It's right here. I'm sliding it right past one another, therefore the failure plane is going to be predetermined. It's going to be along the horizontal line. Do you agree? Is it going to happen in diagonal? Probably not. And that's exactly the disadvantage of this type of test. Because in reality, we know that our soils are not going to fail in horizontal plane. They're going to fail in a diagonal plane. Remember we talked about the failure angle, the theta value, 45 degree plus phi divided by 2. Typically, a phi values that we talked about for a compacted material ranges between 30 to 40, somewhere around that. So you know that the failure angle is going to be 45 degree plus, say for example, 30 divided by 2. This is going to be diagonal. This is predetermined, right? This is going to be horizontal. All right, so this is essentially what we have in terms of the direct shear test. But let's quickly talk about the parameters there and how we can get the C and phi values in general. All right, so let's quickly take a look at our direct shear test. It consisted of 2 stages of loading. We call this P as surcharge, or your normal stress in this case, if you will. And this is going to be that shearing forces that Alright, so these are going to be different amount of weights that you place at the top of the soil. Right? It could be 100 grams, 200 grams, 400 grams. And the higher that number would be, the better would be the interaction between the particles. Essentially compacts the material underneath that weight. So weights applied on the surface, or at the surface. And surcharge acts as confinement. Higher surcharges, higher weights, results in better interaction between the particles, improves the interparticle frictional forces, therefore it improves the shear strength of the soil. And this is exactly that sigma that you see in the general form of the equation. You're increasing sigma, and you know that it's going to be ascending in nature, right? That Mohr-Coulomb failure envelope that we have. All right, so we have essentially two stages of loading. Stage one is application of the surcharge. What is stage two? Now you apply the shearing force by imposing a certain amount of deformation. Horizontal, right? So that's how you take the material to failure. So from this point on, any type of test that we talk about, we need to make sure that the material fails, right? You need to make sure that the magnitude of the stresses are high enough that results in the failure of the system. Because we are interested to determine points along the failure envelope. And any point along the failure envelope represents failed material, right? Alright, so we have two stages of loading. Stage one, application of the surcharge. Stage two, application of the shearing force. And once you get those two values, you can simply calculate the normal stress and shear stress. Alright, tell me how you calculate the normal stress. Let's go one step back. What is the objective? The objective is to find C value and phi value, right? For that, I'm looking at my Mohr-Coulomb failure envelope. Right? What do I have on the y-axis? Tau, right? What do I have on the normal? Normal stress, right? Or horizontal stress, we have the normal stresses. So what is my normal stress? Load divided by area. You have the weight, right? The surcharge is going to be normal, right? It's going to be perpendicularly downward. And the area that resists that. From the top is going to be that segment here, right? So this is going to be the area that resists that normal load. Now, how do I calculate the shear stresses? This would be the shearing resistance in the horizontal divided by the area that resists that, right? So those two components are required to be able to find those points along the failure end. So for that, it's very simple. Magnitude of the surcharge divided by area, P over A, gives you the normal stress. On the other side, what do I have? I have the shearing force, or resisting shearing force, right? Because basically it resists the sliding of those two half boxes, if you will. And then there is going to be an area that resists that, divided by the area. So in both cases, your equations are very simple. It's basically load divided by area in both cases, right?
You don't do any corrections for the fiction of the plate?
No crushing is considered up until graduate level. Everything is assumed that everything is associated with rolling of the particles. All right? Any other comments? All right, so this is basically what we have in terms of the general form of the equations. Alright, so here's what you have to do. How many points required to plot a line? 2. But we typically have to run at least 3 points. Because we are basically running the best curve or best line through them. Because if at some point you have some numerical mistakes, something along the lines of making some mistakes in the lab during the process of testing, we want to make sure that we're accounting for that. So here's what you have to do. You have to run it at 3 different confining levels. How do I replicate my confinement? Based on the surcharges, right? So here's what you have to do. You have to run it at 3 different surcharges, 3 different weights. So incrementally increase that, 100, 200, 400 grams, right? That results in different failure, different tau values. And ultimately that will result in those 3 points. So let's talk about that and see how you can get those 3 points. Let's assume I'm looking at my stress strain curves. So I have my stress strain curves. I'm assuming that in all 3 cases, I compacted the material. So let's see what we have. You have P1, which is the weight of the first surcharge, divided by the area that resists that. P2 is the second surcharge, which is going to be higher or lower? Higher or lower? Higher or lower? Higher. That's good, right? You get more participation. And how about P3?
Higher.
Highest among the 3, right? Higher would be the confinement level, the higher would be the strength of your soils. So what this means is that in your exam, if I ask you, tell me the relationship between the level of confinement and the strength of the soil, this would be what you have to plot. Basically, it tells you that P3 is greater than P2 is greater than P1. You agree with that? Sigma 3 is greater than sigma 2, greater than sigma 1. Yes. So the higher would be the level of confinement, the higher would be the strength of the material. So I'm looking at the shear stress versus shear strain in this plot, obviously. What is the peak of the stress strain curve? Peak of this stress strain curve is called mechanics of materials. Strength of the material. This is your strength. That's the reason that I put that as tau sub f. Right? So tau sub f, the peak of the stress strain curve, represents the strength of your material, right? So you have higher strength for the curve that is higher than that, and then you have lower and lower in that cases. So that basically signifies the role of the confinement on the strength of the material. Alright, so this is what I get from the direct shear test. How can I plot my Mohr circle?
That's the radius on the
Now, so first tell me, do I have points that fail?
Yes.
What are those points?
Sigma 1,
So I put them as 1 would be sigma 1. That way. Now I have 3 points, which represents the filter. So if I go back in my sigma versus this could be point 1, 2, and point 39. Do you agree? So you run the best line that results in the mean square error between those two. Trend line in your Excel spreadsheet. That's how it works. Yes. Now you have the points that are basically lying along the failure surface or failure angle that you have. Now the rest of it is going to be very simple and straightforward. You have the C value here and you have the phi value here. And those are the parameters of your Mohr-Coulomb failure. That's how you determine that. Make sense? So that's basically the process. The process is we have to run 3 tests, probably with replicates, meaning that you have to run it twice. Right? Each stress is fixed. And then the first step is apply the surcharge. We call that applying the confining pressure. The next step is take the material to failure. Why to failure? Because we are interested in points along the failure envelope. We are not interested in points that are contained below the failure envelope. That doesn't give me that information that I'm looking at. So you're looking at the C values and the phi values to be able to characterize the Mohr-Coulomb failure envelope. You need to know the C, you need to know the phi value. For that, you have 3 points, 3 tests, right? Run at different surcharges. Therefore, based on that, you can simply get the Mohr-Coulomb failure. So if in the question, if in the problem, they ask you to determine the parameters of the Mohr-Coulomb failure envelope, you have to report C value and you have to report your phi value. If in your senior design, you're supposed to determine the strength of your material, in your geotechnical report, you have to locate C value and phi value. Right? That's basically what you have to do when you're looking at the strength of the material. So that's basically the general concept behind the direct to shear test. Alright, so let's quickly go over our lecture notes, and that's basically summarizes all the material that we talked about today. Let's quickly figure out what we talked about in previous lectures, and in the beginning of our lecture, we talked about the general comments and concerns that we have with the shear strength of soil. The strength of the material is the greatest stress it can sustain below, above which the material essentially will fail. Failure is replicated by those failure surfaces or failure planes that we talked about. The soil cannot resist tension. We know that these are frictional materials, therefore if you subject them to tensile forces, you basically compromise the particle contact. So we have to be mindful of that. When the shear stress acting on the soil exceeds the shear strength of the material, failure happens along the failure plane. Again, the failure plane is the plane on which the combination of the normal and shear stresses are higher than the shear stresses and normal stresses that the soil can sustain. The structural strength of the soil is a function of the shear strength of the soil. Remember we talked about the definition. The definition was the resistance of the soil mass that acts against the sliding and failure of the material. Shear strength is required for all these geostructures that we talked about. We need to know what the shear strength is to be able to properly determine the strength of them or design the retaining structures, maintain the stability of the slopes, design of the foundations, and all the other geostructures that are listed in here. Then we talked about the significance of the Mohr circle. Remember, any points that are below the failure envelope, these are essentially represented stress states that are safe. If you recall in the previous lecture, we also talked about the probability of failure. The proximity to the failure envelope represents the higher probability of failure. So that's another way to think about that. Obviously, for this point, it means that the magnitude of the stresses are small enough that it's not going to result in significant amount of deformation in the system. Any point above is impossible, right? There is no theoretical explanation for points above the line. Your material can either fail, which relies along the failure envelope, or be contained below the failure envelope, as we talked about. All right, so in terms of the laboratory test, in our lectures we talk about two types of tests. We have a series of other tests that we're going to talk about, those hopefully in the graduate level courses. But for this course, we talk about the direct shear test as we discussed today, and we're going to talk about the triaxial test. We have different ways to run the triaxial test. Again, more discussion on that would be on graduate level courses. So we'll talk about the triaxial shear test, which is again a strain control type of test. And for the field test, we have a series of field tests to be able to get the strength of the material directly in the field. The most widely used one would be the SPT test, or standard penetration test that we have. We have cone penetrometer, vein shear test, pressure meter, and also the dilatometers there. The first three on the line that you see there are the ones that are typically used in the field. Probably, if you stay in El Paso, the only one that we have here is the SPT test. CPT has a lot of offshore applications and a little bit more complicated in terms of the instrumentation. And then vein shear test is something that if you go outside of the US, you see that a lot of people use vein shear test for characterization of the strength of the material in very fine grain and plastic materials. Alright, so this is essentially what we have in terms of the general flow chart as we talked about. We are looking at the strength of the material in the field, the strength of the material in the lab. For the field, we think about it and talk about it in the graduate level courses. In the undergraduate level courses, we focus on these two tests. One would be the direct shear test, the other one would be the triaxial shear test. Again, remember the objective is to replicate what happens in the field. Again, what that means is that the soil disturbance is extremely important. Make sure that you don't change the internal structure of the soil before running these types of tests. Alright, the process is, for both tests, that first you apply confining pressure. The second step is you take the material to failure. You apply the stress state that results in the failure of the material. So there's a two-stage loading system that we have, and this is the same for both triaxial tests as well as the direct shear test that we have. But the way that we apply the confinement in these two tests are entirely different from one another. So for the direct shear test, the way that we apply the confinement is based on the surcharges, right? So the higher would be the surcharge, the higher would be the strength of the material, right? Because we had sigma in the general equation, tau equals to C plus sigma times tangent of phi, right? And the higher would be the sigma, the higher would be the tau value, right? Tau was the shear strength of the soil, actually. And that was the equation of the line. Therefore, it falls along the failure line. Alright, so we have a two-stage loading system as we have. In this case, your sigma V would be your normal stress in the vertical format. And then you have the shearing forces that will develop along the failure plane, and that has to do with the imposed deformation, right? Remember, we basically have two types of tests. One is called the stress-controlled, the other one is called the strain-controlled. The stress-controlled is very simple. You apply the stresses and you measure the strains, right? Therefore, you control the stresses, and that's why it's called the stress-controlled. On the other hand, we have strain-controlled test, meaning that you apply the deformation, or you impose the deformation, and you figure out the external stimuli in the system. And that would be the development and the stresses in the material. So in very simple terms, if I induce a deformation per minute, we talked about that, 0.02 millimeter per minute, for instance, that will result in the resistance of the soil up to a certain level, and beyond that point, your material will shatter, will fail, right? So that's basically what we are interested in. These tests that we are talking about here is strain control, similar to what you know about unconfined compressive strength for concrete. right? This was the same thing. You induce a deformation, and at some point you see the breakage failure of the material. Same concept there. But once we start talking about the resilient modulus test and all the other type of tests that we have specifically for the soil, those are the type of stresses, those are the type of tests that we control the stresses, and we measure the strain along it. So that's how we develop our stress-strain curve in those cases, and we figure out what are the responses to the loading that we have. All right, so this is the famous shear box that we talked about. It's split in half. It can freely move along the horizontal plane, and you induce the deformation along the horizontal plane. And this is the main disadvantage of this type of test, and that's because of the fact that the failure plane is already determined. We know where the material will fail. The other disadvantage that this test has is the non-uniform distribution of the stresses along the failure plane. So that's another thing that we have to be mindful of. This is the different types of the different components that we have in the direct shear test. On the top left-hand corner, you're looking at the way that we compact the material with that tamper there. Then you do have the material right here, the support here. You place the porous stone at the top, and you place the surcharge at the top of that. And at the top right-hand corner, you see that deformation that is induced by the system, by the data acquisition system and the loading system that we have. These are the stages of loading that we have. This is a schematic way to look at that. You're looking at the steel ball and the pressure plate. That would be the surcharge that we have here. And it can freely move along this plane. Once you apply the second stage of loading, which is the shearing force, these two move along one another, and you'll be able to calculate the stresses and strains associated with the loading conditions that we have. And these are the only two equations that you need to know in order to calculate that. And it's very simple. It just basically tells you that divide the force by the area, and you know how to do that. It's very simple, and you get those values, and based on that information, you can develop your Mohr-Coulomb failure envelope. And the objective would be the C value and the phi value. All right, so let's just stop here. When we come back, we'll talk about the different behavior of the compacted and loose materials, the dilation of the materials, and ultimately the last one would be looking into the triaxial.